This is a very short lecture, the topic being on units used in physics, with more emphasis on units of electricity and magnetism. So let us go to SI units versus Gaussian units. Right from our childhood, we came across certain units which are mostly mechanical, namely length, mass and time. The units being centimeter or meter for length, gram or kg for mass and second for time. By now you might agree that the unit of time troubles you the least because it is second in all choice of units. Gradually we learn about other units. Notable among them are coulomb, ampere, coulomb being the unit of charge, ampere the unit of current, Kelvin the unit of temperature, mole the unit of amount of matter, etc. In any physics course, it is proper to start with two powerful things. One is principle of dimensional homogeneity that says a very trivial but very important thing, that the dimension of both sides of an equation should be same, and we have to follow this to say something sensible or meaningful. And the second one is a judicious or clever choice of units, so that discussion that involves measurements, specifications of various quantities is done in a meaningful way. So comes the very important question, which unit shall we work with? In this class, we are not going to discuss any bit of history but go straight to the topic. In my experience, whenever a physics student goes to study magnetism, he or she, if not cautious, is bound to feel like being trapped, and the subject will appear to be unmanageable and sometimes depressing. Better to decide at the very beginning which units one should use. Now people across the globe, that is almost universally, use SI units, be in engineering or in science or elsewhere. You will understand why other units are terribly losing popularity at the end of this lecture. When we were students, someone told us physics goes with Gaussian units or Gaussian system, and it did so for many years, even centuries. What that someone said was indeed correct, but as we now find, we should never look back and adhere to a unit that is complicated, confusing, and to many it seems funny, and so it is losing the battle with SI unit, which is extremely popular, easy to use, systematic and scientific in the true sense of the term. Another reason for this lecture is that even now some people use Gaussian units, and in a few exams questions even are set in Gaussian units. Sometimes various lectures are given in Gaussian units. So one should have at least preliminary idea of Gaussian units. SI unit is called International System of Units, and it has 7 components, while Gaussian units was invented by Heinrich Hertz in 1888, and it was named after the famous scientist Gauss. In Gaussian units, the mechanical units are centimeter, gram and second. Now let me state the purpose of this unit as envisaged by Gauss. Gauss was of the idea that mechanical units should be chosen as fixed and the basis for all measurements. Even electromagnetic quantities are to be measured in terms of mechanical units. Obviously, it was a great idea and was driven by the urge to make things simple. In contrast, SI system has 7 units, and we cannot think without Coulomb or ampere. When we are talking of electric field or magnetic field or current, and in such situations we have to bring Coulomb or ampere in addition to the mechanical quantities, mechanical units. Let us discuss Coulomb's law in Gaussian system. So this is the form, and we can easily check the dimensions. So this has the simple structure, and from which we end up with Q square equal to F into R square. So from here we end up with this simple relation, charge equal to under root energy into length, a huge relation, and we find charge has been completely expressed in mechanical quantities, energy into length whole under root. Now Q is under root F R square, so F has mLt to the power minus 2 and R square is L square. So simplification gives us this thing, and therefore charge can be expressed as gram to the power half, centimeter to the power 3 by 2, second to the power minus 1. Now this is unthinkable in SI system. The unit of charge in Gaussian system is stat coulomb. It is written as stat C, C for coulomb. In Gaussian system, the electrical quantities are addressed as follows. The electrical quantities, they are expressed in ESU, and magnetic quantities are expressed in what is called EMU. Now when we speak of charge, it falls to this category, and the unit of charge is stat coulomb as mentioned earlier, and 1 stat coulomb is this much coulomb, or 1 coulomb is this much stat coulomb. This is the conversion factor. Now the problem starts when we go to the unit of current. Current involves charge, and charge means there is an electric field associated with it. So current will have an ESU, and it is called stat ampere. Again, current means charge in motion, and current is associated with a magnetic field, so definitely it will have an electromagnetic unit which is called ampere. So we arrive at a confusing situation, current having unit both in static situation as well as in moving situation. So we have a stat ampere and ampere, and the conversion factors are given over here. Now which one to use is something of a bother, and it is very difficult to decide. It is very disturbing sometimes to decide which unit should we use. Let us now do a particular problem, and then we'll come back to the main discussion. We'll find how much Gauss is 1 Tesla. Tesla is the unit of magnetic induction, so is Gauss. Tesla is in SI system and Gauss is in Gaussian system. Now, as we did in lecture 1a, 1 Tesla is 1 Newton per ampere per meter, and we can put the dimensions to end up with kilogram per ampere per second square in SI system. Now we can easily transform to Gaussian system, and using these conversion relations we get to 1 Tesla 10 to the power 4 Gauss, which we also did in this lecture. Now let us point out certain things. The relation between Gauss and Tesla should not be expressed as equations. Here the manner we did appears that we have used some equation, put this for that, and ended up with an answer, and this technique is not really proper, because Tesla and Gauss are mere correspondences. Gauss can be expressed using only mechanical quantities, while Tesla cannot be expressed through mechanical quantities only. We have to bring electrical quantities into the discussion, otherwise you cannot define Tesla. So this means this way of obtaining at some relation is not justified. We will come soon to the most disturbing as well as funny side of Gaussian unit, which I feel is the reason for its unpopularity. But before that, let me place certain important equations whose form in SI system and Gaussian system are different, and for ready reference I am putting them. Sometimes we come across laws and equations written in Gaussian units and we search for the corresponding SI format. Now in this chart many quantities will come up which will be discussed, defined in various lectures in the series of Magnetostatics and Electromagnetics. Here we just make a collection and place some relevant equations. So this is the Lorentz force equation in SI and this one is in Gaussian. Look at the V by C factor. Here it was just V. So the structure is different. The famous Maxwell's equation, this is the first equation, second equation, third equation, and this is the fourth equation. But in Gaussian system, their structures are different. Only the second equation, which corresponds to Gauss law of magnetostatics, is same. Divergence B equal to 0. So apart from second Maxwell's equation, all other equations undergo change in form if we shift from SI to Gaussian or from Gaussian to SI. These are the constitutive equations which interrelates various electrical and magnetic quantities in the two systems. Notable here is in Gaussian system D, E and P, they have same units, but in SI system E has different units and D and P they have same units. In Gaussian system B, H and M they have same units, but in SI system H and M have same units but B has different units. In Gaussian system we have no epsilon 0 and mu 0, but here we have epsilon 0 and mu 0 representing permittivities of free space, and this one is permeability of free space. This sheet gives definition of various terms that are used in Maxwell's equation. Here these quantities are used in writing or framing various equations of electricity and magnetism. This sheet represents various laws in Gaussian and SI system. Coulomb's law, here the electric field, electrostatic potential and the Poisson equation. The Biot-Savart's law, magnetic vector potential. These are the electric and magnetic fields in terms of vector and scalar potentials. Pointing vector is here. Field momentum density, field energy. Here too we have various quantities. These are the gauge transformations and this is the equation of continuity which happens to be same in the two systems. In this class we are not bothered about the multitude of equations or laws. They are being written or brought into discussion only to compare SI and Gaussian systems, and these laws or equations or whatever will be dealt with, derived and explained in various classes of electricity and magnetism. Here our main concern is a comparison of SI system with Gaussian system and to show that even the structure of these laws are different in the two systems, so we have to be very careful in writing them. Let me now mention why Gaussian system is popular to some. Maybe these are the reasons. If we look at Maxwell's equations, these are the Maxwell's equations. In the Gaussian system, C occurs to the first power. So this simplifies Maxwell's equation by a large amount. Secondly, charge was shown to be equal to under root energy into length. So this is how charge can be expressed. So charge can be expressed in mechanical units, and this is a huge thing. So 1 stat coulomb can be expressed as a combination of gram, centimeter and second. So this is really a great achievement. Another simplicity that Gaussian system infuses is that these field quantities, electric field, electric displacement vector, polarization, as well as B, magnetic induction, the magnetic field strength and magnetization, all they have the same unit. All these quantities, all these observables, they have same dimension, same unit. This is another great thing. Also potential, both scalar and vector, they have the same unit, same dimension. This is evident if we have a look at this equation written in Gaussian system. Grad V is actually del x of V, and if we take C, inside the del we have del Ct, and Ct is just x. So dimension or unit of the denominators are same, and this means V and A are of same unit, same dimension in Gaussian system. So Gaussian system makes things very simple. Let me bring Coulomb's law again into discussion. Coulomb's law in Gaussian system. So this is the Coulomb's law in Gaussian system, and we can write F equal to Q into E. F is the force between two charges and E is the electric field due to one charge, say Q prime, the source charge. So we can write in this way. This is the Coulomb's law. So from here the electric field can be expressed in this way. It is force by charge, and therefore we can write it as dyne per stat coulomb. Now if you put the dimensions and simplify, then we end up with an expression for E, the dimension being m to the power half, L to the power minus half, T to the power minus 1, and if we write down the units, we have gram to the power half, centimeter to the power minus half, and second to the power minus 1. Also, let us recall this thing, E equal to F by Q, and if we multiply by L, we end up with energy in the numerator. Again, energy can be written as charge into potential, so the charges cancel out and we are left with volt by length. So the unit in Gaussian system can be written as stat volt per centimeter. So the unit of E that we end up with is dyne per stat coulomb or stat volt per centimeter, and there is a conversion factor between stat volt and volt. So we have obtained the unit and dimension of electric field in Gaussian system. This is the dimension and these are the units. Now let us come to Lorentz force relation, and this is the Lorentz force relation in Gaussian system, not in SI system, in Gaussian system. Clear that this is velocity of the charge and this is speed of light, so their dimensions cancel out, and it clearly follows that E and B, they should have the same unit, same dimension. So expression of Lorentz force in Gaussian system suggests that E and B have same units and dimensions. Also explicitly we can do it, dyne for force, stat coulomb for charge, centimeter per second, they will cancel out, and we have a B here. So in the next step we have B equal to dyne per stat coulomb, and this one, as we showed, this one is equal to stat volt per centimeter. Now the interesting fact is that the unit of B is given a particular name which is called Gauss. Again, from this relation what we see that B, H and M have same unit. So B and H have same unit, same dimension, but the unit of H is called Oersted, and this is the relation between SI unit and the Gaussian unit of H. And let me now point out the funny thing. The quantities E, B and H all have same dimension, all have same set of units, and this we have proved. Yet Gauss is the name given to the unit of B and Oersted is the name given to the unit of H. So this is something which is difficult to comprehend. In spite of being identical, they have different names. So Gaussian system is somewhat difficult to get along with. There are reasons therefore for SI system to be popular. Before ending, let me present how to convert from Gaussian to SI. So if we come across an equation which is written in Gaussian units or a law expressed in Gaussian system, now since we are doing things in SI, we have to convert it, we have to get to the corresponding expression in SI system, and this can be done through these substitutions, and there are many of them. I have only written 4. Let us do 2 problems. One is convert to SI this one. So this is actually Coulomb's law in Gaussian system. So as per our prescription, if we put this one for Q, then what we have is this thing, which is the SI form of Coulomb's law. So we can easily convert from Gaussian to Coulomb through these substitutions. Let us try to convert this equation, which is the famous Lorentz force law written in Gaussian system. So again, if we put these things, then we end up with the SI form of Lorentz force law. Another very important quantity is the fine structure constant. Fine structure constant is expressed in Gaussian system as E square by h cross c. C speed of light in free space, h cross is h by 2 pi, h being Planck's constant, and E is the electronic charge magnitude. The SI form can be obtained if we put this thing for Q. Here Q is E. If we take this square, we end up with this form. So the form of fine structure constant is this one in SI system, but in Gaussian it was this one. And from here we can go over to here through these substitutions. Before ending this lecture, let me state therefore that there are reasons for SI system to be popular, and it is better, safe and helpful to use SI. It won't betray you. But to use Gaussian system, you require a lot of skill, knowledge and expertise to overcome these strange, curious, odd features that hides underneath it. Let the world belong to SI. I will conclude this lecture with the famous statement of Einstein: everything should be made as simple as possible, but no simpler. Thank you.